Okay, in this video, we're going to look at a couple synthesis examples. So I think it's important when you're approaching a synthesis problem to always ask two questions. The first one is to note whether there's a change in the carbon skeleton, right? Did we gain or lose any carbon atoms? Because there are only a couple reactions that we know so far that can achieve those changes. So that'll give us some insight into the types of reactions we're going to need to use, right? And then also we want to be sure to note whether we've changed the identity or the location of any functional groups. And so really, to get good at solving these synthesis problems, you've got to know all the reactions that we've covered this semester. And then I think it's really important to practice. And so working lots of example problems and being sure that you know all of the reactions is the key to being successful. The book talks a lot about retrosynthetic analysis, and I think this is useful in part. Now, the book has a very formal way of doing it, and it'll say, when you're going from the products to the intermediates, they're sort of, working it backwards and they're using these sort of double arrows. I don't find that that's particularly useful. But what I do think is useful is that very often it's helpful to work backwards and sort of think about the later stages of the reaction before the forward stages of the reaction. But that's not always the case, and I think oftentimes what you'll find is the best thing to do is to kind of work in both directions. So work both backwards and forwards until you sort of meet in the middle. Okay, here's our first example. And so what you may want to do is pause the video and see what you can come up with and then compare that with what I get. And it's entirely possible that you come up with a different strategy than the one that I employed. I think you're going to find that oftentimes there's more than one right way to achieve these syntheses. But when I look at this problem, the first question I ask myself is, did I change the carbon chain? And so in my reactant, I started with 1, 2, 3, 4 carbons. And I've got 2 methyls coming off this second carbon. And I have 1, 2, 3, 4 carbons, 2 methyls coming off the second carbon. So I didn't change my carbon skeleton. So then the next question is, what happened to the functional groups? Well, I think the position didn't really change, but I turned the alcohol into an alkyne. Now, I think on this problem, the retrosynthetic strategy is helpful, right? Because there's all kinds of reactions that I could do to this alcohol, but we only know one reaction that can make an alkyne, and that's the double elimination of an alkyl dihalide. And so I think the last step would have been something like this. And so if I put 2 bromines on here, and then the reagents I would use to get from that alkyl dihalide to the final product would be to first hit it with a strong enough base. And because it's a terminal alkyne, we'd also need to react it with water to reprotonate that alkanide ion that we would make. All right, now, how do I make an alkyl dihalide? Well, I think the reaction we learned to do that would be bromination of an alkene. So in order to go from here to here, if I reacted that with Br2, I think we would accomplish that change. And so now I think I'd kind of work forward. And so I want to say, okay, well, how do I get from here to this alkene? Well, if I could do an elimination reaction, I could get from this alcohol to this alkene. But we remember that OH isn't a good leaving group. But if I react that with these reagents, I can form the tosylate, which is a good leaving group. All right, and then finally, now that I have a good leaving group, to do the elimination, we want a strong base and ideally a weak nucleophile so that we don't, because it's a primary leaving group, if we use something like sodium hydroxide that's a strong base and a strong nucleophile, that's going to give me substitution products as well. So from our list of strong bases weak nucleophiles, we've got sodium hydride, or the DBN, or the DBU. So let's use sodium hydride. And so I think we have now achieved the synthesis. And so we could put in that, or we could write down now our list of reagents. So first step, in the solvent. And then the second step, sodium hydride. Then if we react that with bromine, and then for the last part, the strong base, and then water to accomplish the proton transfer. Okay, here's our second example. So again, our first question, what did we do to the carbon skeleton, if anything? And so in our reactant, we have 1, 2, 3, 4 carbons with a methyl coming off the second carbon. We have 1, 2, 3, 4, 5 carbons with a methyl coming off the second carbon. So we did alter our carbon skeleton. And so I think this is in the case where we're either going to use terminal alkylation or the Gilman's reagent. And so I think I'm going to try using the termination or the alkylation of a terminal alkyne. So in order to do that, if I wanted to do the terminal alkylation, I need to have an alkyne. So if I had an alkyne here, we could then add a methyl group to it. And so to get from, so the previous compound of this, if it's going to be an alkyne, I have a trans alkene. And so we know to go from an alkyne to a trans alkene is going to be liquid metal reduction. So if I go backwards, use sodium and ammonia, the reactant would have been this compound. Okay, and so now to get from the 5 carbon atoms that I have here to the 4 that I started with, for the terminal alkylation, if I used NaNH2, and then I need an alkyl halide, so if we used methyl iodide, then that would have come from that compound. Okay, so now comparing here to here, we need to have made an alkyne, and then we're also going to have to move the double bond over. So to make this alkyne, right, if I reacted NaNH2 and water, that would have come from this alkyl dihalide. And then this alkyl dihalide could have come from this alkene. And so the way I would have gotten between those two would have been with bromination. All right, and so now my task is I've got to move this double bond over. And so I think there are a couple ways to do that. I think if I add HBr via anti-Markovnikov addition, so we do HBr, and in the presence of peroxides, then I'll get the anti-Markovnikov addition. And so the bromine will go there. And then to get from here to here, I want to do elimination, but I want to get the Hofmann product, not the Zaitsev product. And so I want to use a bulky base And so if I use tert butoxide, I think I can achieve that change. And so if we collect all of our reagents, so in our first step, HBr in the presence of peroxides, then I hit it with tert butoxy, then bromine. In this step, we need to add, first the strong base, then the water. So 4 will be NaNH2. Then we'll react it with water. Then we'll do the terminal alkylation. With methyl iodide. And then finally, the dissolving metal reduction. All right, I've got one more example on the next slide. Okay, so one final example. So we check our carbon chain. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. So obviously we've increased the carbon chain. And so we're either going to use the terminal alkylation or the Gilman's reagent. And in this case, if you notice, we've essentially just doubled our starting compound, and we've connected them together. So this seems like a good case to use the Gilman's reagent. And so to do that, if I react this with 2 equivalents of lithium, and then half an equivalent of copper 1 iodide, that's going to give me two of these attached to the copper lithium compound. And then to get the final product, I need to react that with an alkyl halide, and I can just use the starting material. So if I react it with this guy, then it's going to couple my 2 compounds here and here, and I'll get the final product.